the nature of sound. So remember, sound is a longitudinal wave that can travel through a medium. So, and like all waves, it needs, well, not like all waves. Like most waves, it needs a medium to travel through. A sound is caused when a source creates a disturbance in a medium. So sound can only be created by some sort of disturbance within a material. It can be like hitting something, it can be speaking, that's a disturbance in the material of air. The particles of the medium get compressed by the source. Anytime, all you have to do in order to make a sound is create an air pressure differential. So your voice, that's your vocal cords, are vibrating the air, creating an air pressure differential where you're forcing air through a closing and opening aperture. So if we wanted, I did talk about this for a second, but if we wanted to visualize a sound coming off of a cord, yeah? A sound coming off of a cord, we have a string. I'm gonna use two colors. And there's air around the string. You bend the string, you pull the string up and release it. And that makes the string sort of hit, like so I'm like imagining it's back, this is its bounce back. So the string has sort of like pushed a bunch of these particles over here, leaving less particles over here. So these particles on the bottom are just like left over, that they haven't been hit. They're not creating a vacuum, you're just creating a lower density of particles here. And the particles on the top have been sort of like shoved up by the energy of the string moving. And then the string bounces back. But these particles have been like hit and are going that way. And there's this kind of like less dense place. And the string will have like collected particles down here, pushing it those way, and they're going that way. And the string will bounce back and forth doing this. So let's make it go back on its travels again. So these first hit particles are now up here, and you have a new band of denser particles with like light density between them moving. So that's the wave. That's the like peak, valley, peak. And so there'll be less dense here and a denser band of particles going that way. And eventually, string, vibrate, vibrate, you'll have like these bands in a curve of denser air with like less dense between them in both directions. So these have names. These are the increased pressure parts and the distance between a condensate, or the distance between condensations, that's the period, or between rarefactions, that's the period. One condensation plus one rarefaction is one cycle. So if you're talking in distance, one condensation plus one rarefaction would be the wavelength. If we're talking in time, one condensation for one rarefaction, that would be the period. Depends what we're talking about. The frequency of a sound wave is how many cycles occur in 1 second. A sound with a single frequency, which doesn't happen that often, however. Most sounds are built up of a couple. A sound with a single frequency is called a pure tone. They're sort of unnerving. Pure tones are a little like creepy feeling. I don't know how to explain it. Healthy young people, healthy young ears should be able to hear and 20,000 hertz. We don't have a terrible range, actually. We're not like dogs, but like that's not too bad. Like that's pretty low and pretty high. Like other things might have like way, way, way higher than we do, or way, way, way lower. So your parents' age probably. Are about 20 to 12 or 14,000. So you lose a very, very, very large amount of your upper range. So if you ever experienced like where you hear a really high pitched thing and your parents like, what are you talking about? I can't hear it. They actually can. Yeah. Like that's why they have those annoying text messages that like you can text without your teacher knowing because it'll go really high pitched. Or like there are companies who have anti-loitering, or there were. I think it's like gone out of fashion now because it's like genuinely painful. There were companies who would like so that teens would hang out in front of their stores. They would just like blast 20 hertz. Oh. So like if you were like going to be annoying and sort of loiter in front of the stores, it would just be like, wow, it's really painful here. A use of a pure tone. We don't use pure tones that often. But if you encounter a dial, the like touch dial phone. I don't know if people still have home phones. But this is what home phones look like. I remember you fondly. 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. I think this one's star and this one's pound. The way this was designed, the actual notes that play, like I can know if I dialed my like middle school best friend by ear because it like there is a tune you play when you're like and it's known because it is always the same. They did this, so each note is a combo of 2 pure tones.
Yeah, I noticed that.
And so you can actually hear like in a column, they'll sound sort of similar because they have the 1336 hertz, but then it'll go like, like you'll be able to hear like families of tones. So you can, without looking, or this was, I think, originally designed to help like blind people be able to dial. Because like you can hear it, so you know like the right tones. But yeah, that's a use of, so it's two pure tones combined, and they're always the same. They're easily distinguished and they're related. There was an entire world, some of the first like big deal hackers. There was an entire world where you would call into numbers and like if you wanted to call abroad, you would call into a number and then they would like put you through, right? Not an operator, but like basically like a switchboard. And a lot of hackers figured out that the way the switchboard like did the work and put you through is through like a series of tones. Really? And they figured out like if you picked up a public phone and then played tones into it, you could like call important people or call Paris for free.
That's insane.
And even I think early internet, like early dial-up, it was basically if you did like it would just like do it for you, and it thought that it was getting the right input because it was looking for these pure tones. Sound below human hearing, which for the record is not below human experiencing. It's called infrasonic. Just like infrared, I think below our ability to see. Infrasonic things usually you feel it, like that, like ooh, in your chest. You might not be able to hear, but like you feel. Elephants communicate infrasonically. Yeah. Whales communicate infrasonically. Infrasonic is really good for long distance. So long distance low differences. So like if you want to go long distance, but all you're trying to say is like, hello, like that works. Above is called ultrasonic. You'll notice infrared, ultraviolet, infrasonic, ultrasonic.
Nice.
Ultrasonic, that's echolocation, that's dog whistles. This is good for lots of information. So that's why it's good for stuff like echolocation, because if you're a bat, imagine you're a bat, and you're sending out like just a ton of information, versus if you're an elephant, you're sending out like that. So this ton of information, when it bounces back, is a ton of information, whereas when this returns to you, some of this might not even return. Like sometimes it's like a sound wave hits something and deflects. So like maybe this one won't make it back to you. And then you have two information out of them. This, you can get thousands of information, right? I mean, it's above 20,000 hertz. So it's above 20,000 cycles per second. So you get tons of information from like 40,000 cycles per second. You're getting, like, if you just use a little for 3 seconds, you get 120,000 cycles worth of data. So if you need to know immediately where something is, like dolphins, for example, right? Dolphins need to be able to like very quickly change locations. They are hunting fast things. If you are hunting fast things, you need to be able to. If you are big and slow, and your biggest thing is, hey, is anybody nearby? And by nearby, I mean within miles, then all you're really doing is like, yo, and then another whale a ways off might be like, hello, and that's pretty much all they do. Like then you might be like, hello, and then like, that's all you can really get if all you're sending out is like, versus bats are sending out, literally, it would look like, if I was to put this in phase, a bat, it would look like this. Like, you would not be able to distinguish anything. It would just be solid sound. That is how many more cycles there are than wave cycles. So everything about sound is mathematical, but then also how do our bodies interpret it? Some people cannot interpret that properly, which is why they cannot match pitch or hear pitches. That's fine. It is a subjective frequency. The note would not change its frequency just because you can't tell what it is. That's another thing that is definitely subjective, right? Like you might have your headphones in and be like totally comfortable, and your friend might put them in and be like, God, that's loud. Right? It is subjective interpretation. So pitch and loudness are not scientific concepts, but they are linked to scientific concepts of amplitude and frequency. They're sort of the objective, we didn't talk a lot about this with mirrors and lenses because there wasn't some time, but like there is an objective thing of color, right? Like wavelength is not objective, but color is. It's not subjective, but color is. Like there are people who are like, I don't see that as a green. I see that, right? That's a stupid blue and white, black and gold, whatever that was, blue and gold dress. The dress. And like how you see stuff is totally subjective. And some people, like there are people who have a fourth color receptor in their eye, called tetrachromatic. And tetrachromatic people can see colors that like you cannot imagine. They see colors you can't. I hope everyone has an amazing spring break. If I'm going to see you next week in other classes, I look forward to it. If I'm not, relax, rest, get some nice outside time, and I will see you when we get back.